section 14.3, double integrals and polar coordinates. So I want to start off with a reminder about our conversions from rectangular to polar coordinates. So I want to be able to review over how to use polar coordinates to describe our regions. If we have a semicircular region with a radius of 2, in rectangular form, this would be y equals to the square root of 4 minus x squared, but in polar form, r is between 0 and 2, and our theta is between 0 and pi. If we have two concentric circles, and I want the region in between the two circles, and let's say the two circles have equations x squared plus y squared equals to 4, and then x squared plus y squared equals to 1. In polar form, this would be more easily described as r is between 1 and 2, and theta is between 0 and 2 pi. One last one, if we were to have a circle symmetric to the y-axis with a radius of 1, this would be x squared plus y minus 1 squared equals to 1. But in polar form, we would think of this as r is between 0 and 2 sine theta, and theta is between 0 and pi. First, let's work on evaluating. So the integral from 0 to pi over 4, the integral from 0 to 4 of r squared sine theta cosine theta dr d theta. So notice how we have dr d theta. We have 1/3 r cubed sine theta cosine theta from 0 to 4 d theta. Now we need to plug in our 4. So plugging in the 4 gives us 64 over 3 sine theta cosine theta d theta. And now integrating again, we can do a u substitution. So if you need to write it out, you can. U equals to sine theta, du equals to cosine theta d theta. Sine squared theta, because the derivative of the sine is a cosine, I need to divide by 2, so I have 32 over 3 sine squared theta from 0 to pi over 4. And plugging in my pi over 4 gives me 1 over 2 minus 0, and I have 16 over 3. Now there's a theorem for changing of the variables to polar form. So this says that if you have some double integral in rectangular form and you want to change the integral to polar form, where you'll have f of r cosine theta and r sine theta, you're going to have an extra r included with your dr d theta. I would actually like to show this to you. If you have a curve, if we looked at a small enough region, then we could approximate this curvy section with this arc, where this is my region r. Here we have some delta theta, and over here we have some delta r, and we can say that this first one is going to be r1, and this second one here is going to be r2. This little piece right here has an arc length equal to s equals r theta, and since the area is equal to 1/2 r squared d theta, it came from looking at this as a little triangular piece, which was 1/2 base times height, but the base is r times theta, or our arc length, and the height of it is equal to r, hence the 1/2 r squared d theta for theta infinitely small. And I'm going to let r equal to r1 plus r2 over 2. So if I plug those in, I'm going to have area of my region r is going to be 1/2 times delta theta r2 squared minus 1/2 delta theta r1 squared, and I can factor out my 1/2 delta theta to leave myself with r2 squared minus r1 squared. And I can rewrite this a little bit and say that I have r2 plus r1 times r2 minus r1, and I'm going to go ahead and take away this 1/2 and place it under this piece. So now I have this as my r. This is going to be a delta r, and this last piece is my delta theta. So here I have my area equaling r delta theta, which is my r dr d theta. So here I have an integral in rectangular form. I will need to convert this to polar form. Now let's take a look and see what this region looks like. Y is bounded between 0 and 2, and x is bounded between y and square root of 8 minus y squared. So y is bounded between 0 and 2. X equals to y, which is a diagonal line. You may want to write this out as x squared equals to 8 minus y squared, and then move it over and you have x squared plus y squared equals to 8. This is a circle with a radius equal to 2 radical 2, or radical 8. So that means I have a circle, and it actually happens to cross at this point, because I know that this is 2 and this is 2 over here. So that makes my hypotenuse of this little rectangle or triangle right here 2 radical 2. So my rectangle needs to have y on the left hand side and then the circle on the right hand side. So the line on the left hand side and the circle on the right hand side. So all of my sections are like this, and the region that we're talking about is this wedge-shaped piece over here. How could we translate this into an equation in polar form? Okay, so I need to first rewrite square root of x squared plus y squared into polar form. Square root of x squared plus y squared equals to just r. And then my dx dy needs to become an r dr d theta. Make sure you remember that there's an extra r dr d theta, so we will end up with an r squared. Now our bounds, d theta is going to go from 0 to pi over 4, because that's the angle created here. And then our r's are going to go from 0 to its radius, which is 0 to 2 radical 2. It's going to be 1/3 r cubed, 1/3 times 16 radical 2 d theta, and then I'll have a 1/3 times 16 radical 2 theta from 0 to pi over 4, which is simply 16 radical 2 over 3 times pi over 4, which simplifies out to 4 radical 2 pi all over 3. Let's use a double integral to find the area of the region enclosed by this Limaçon. R equals to 1 plus cosine theta. We're just going to find the area. This isn't volume, so the area tells me that f of xy equals to 1. So I'm simply going to have an r dr d theta in here. So our theta, what is the theta interval of this Limaçon? It's 0 to 2 pi. Now what is our r? Remember, r is the directed distance from our pole to the curve. So each little section that is drawn always starts at 0 and it ends on r, which is our function. So it's going to go from 0 to 1 plus cosine theta. Now we're just going to integrate this. 0 to 2 pi. So the integral of r is 1/2 r squared from 0 to 1 plus cosine theta. So we have a 1/2, then we need to plug in 1 plus cosine theta, which is 1 plus 2 cosine theta plus cosine squared theta, 0 to 2 pi, 1 plus 2 cosine theta plus 1/2 times 1 plus cosine 2 theta d theta. Okay, I trust that you guys can finish this. When you plug everything in, then you get 3 pi over 2.